Good morning friends. Today I am going to talk about the particle in a box, and this is one of the important topic in quantum mechanics, and the other names of this topic are particle in infinite potential well and particle in one dimensional box, and this is one of the application of Schrodinger's equations in quantum mechanics. Here our aim is we are going to find out the eigenvalues and eigen function, and at the same time we are going to find out the energy of the particle. Okay, so here for that purpose let us consider a particle within a one dimensional box. Here let us take a particle is there in a one dimensional box. Okay, only x axis is there. Here x is equal to the 0 to the x is equal to the L. Here there are two walls of the box are there. The x is equal to the 0 initial position and x is equal to the L is extreme position. Here the potential of the particle is 0 when the particle is inside the box, and of course there is no probability for finding the particle outside the box, so that's why what the potential of the particle is infinity. So that's why x is less than 0 and x is greater than 0. That is nothing but the outside the box where the potential of the particle is infinity we have to consider. And according to the quantum mechanics, we know that the wave function having some properties, that is psi should be continuous, psi should be finite. So that's why we wrote that since wave function psi has to be continuous, it follows that dou square psi by dou x square must be finite everywhere. As the particle is always within the box, here as the particle is always within the box, the probability of finding the particle outside the box is 0, of course. So this implies that psi is equal to 0 everywhere outside the box. So there is no particle outside, so psi wave function is also equal to the 0. So inside the box the Schrodinger equation can be written as. So first we have to apply the Schrodinger equation to find out the energy of the particle in a box or in a one dimensional box. So for that purpose we know that dou square psi by dou x square plus 2m by h bar square e psi is equal to the 0. So let us take this is equation number 2. Here we have considered the potential. Let us take that is equation number 1, and this is equation number 2. Now let for only simplification or easy simplification purpose we are removing this 2m by h bar square e by k square. So let us take this is equation number 3. We get dou square psi by dou x square. So substituting the value of k square in the above equation, we will get dou square psi by dou x square plus k square psi is equal to the 0. So let us take this is equation number 4. So this is in the form of a differential equation of second order. We know that the differential equation having a solution of in this form. So that's why the general solution of the above equation can be written as psi is equal to a sin kx plus phi is equal to plus phi. Let us take this is equation number 5. Here a is the constant and phi is the constant. To determine the boundary conditions, we have to find out the values of a and phi. Now we have psi is equal to the 0 at x is equal to the 0. First boundary condition we are applying where x is equal to the 0, psi is also equal to the 0. Therefore equation 5 can be written as, again I wrote this equation number 5. Here in place of psi and in place of x we are substituting the values of 0. So 0 a sin phi. So this is equal to 0. So as a is the constant and that must not be equal to the 0. So that's why sin phi must be equal to the 0 or phi is equal to the 0. So let us take this is equation number 6. Further, in the second situation we have to consider extreme position where the psi is equal to the 0 and x is equal to the L. So that now the equation 5, that equation number 5 can be written as psi is 0 and at place of x we are substituting the value of L. So that's why a sin kl plus 0. Next that can be written as sin kl is equal to the 0 or kl is equal to n pi or k is equal to n pi by L. So let us take this is equation number 7. Now from equation number 3 we can write 2me by h bar square is equal to k square. This is equation number 3. So now we got the value of k. So just simply we are substituting the value of k in the equation number 3. So 2me by h bar square is equal to n pi by l whole square, k square. So this gives E is equal to En is equal to n square pi square h bar square by 2ml square. Let us take this is equation number 8, and this equation number 8 is representation of the energy values of a particle in a box. So for n order, that is for n is equal to 1, n is equal to 2, 3, 4, for different values, what will be the energy of the particle in a box. So the corresponding eigen functions, well, we know that the eigen function we already given, that is psi is equal to psi naught, that is the solution of the second order differential equation, that is psi is equal to psi naught a sine this one, that is a sine kx plus phi. This is nothing but a eigen function. So from equation number 5, 6 and 7 we can write psi is equal to psi n is equal to a sine, and k value is n pi x by l. Let us take this is equation number 9. Now the probability density. So according to the quantum mechanics postulates, probability density can be written as modulus of psi square, or we can write psi star psi is equal to a square. So simply substituting the value of psi, that is a square sine square n pi x by l. Let us take this is equation number 10. Next, obviously the probability is 0 at x is equal to the 0 and x is equal to the L. At extreme position, the probability of finding the particle is 0. So since the particle is always within the box, so the normalization condition. So according to quantum mechanics, the normalization conditions is can be written as 0 to L psi star psi dx is equal to the 1. So psi value is a square sine square, that is a sine then pi x by L. So that is psi star psi can be written as a square sine square n pi x by L into dx is equal to 1. So next a square if you take out, and if you integrate 0 to L sine square n pi x L by dx, then we will get L by 2, and that is equal to the 1. A square is constant, that is we are taking outside of the integration. Now this gives the normalization constant, that is a is equal to under root of 2 by L. This is one constant, we got this value, that is under root of 2 by L. Thus the normalization eigen function psi n belonging to eigen value En is expressed as psi n x is equal to under root of a value is under root of 2 by L sine of k value is n pi x by L. Here this is, let us take this is equation number 11. Here the equation 8 is representation of the eigen values. Here this one equation 8 is representation of eigen values, and this equation 11 is representation of eigen functions for a particle in one dimensional box. Thank you. For more videos subscribe my channel Physics.